Hello, and thank you for tuning into this screencast. This is for our honors calculus class, and what we're going to be talking about today is a continuation of our lesson on finding the max and the min for a particular function on a given interval. So this is a question I pulled from the homework on Delta Math, and I thought I would just work it out. And then the second example that we'll look at in this video has to do with optimization, which is sort of an application of what we've seen here so far this week. So we're given this function that is a polynomial function of degree 4. It's got a leading coefficient of -1. So generally speaking, we know this function is going to look something like this. Okay, we don't know where it's oriented with relation to the x and the y axes just yet. We definitely can find the y-intercept of 10, but other than that, without digging much deeper into it, we don't know. But we don't really care. What we want instead is to consider what are the critical points and what are the endpoints as far as outputs go. So I would make a little chart over here. My recommendation would be to say, okay, well, here's some x values, and let's find the corresponding y values here, and then we'll just see which one is highest, all right? Or lowest, actually, they ask us for the minimum, so we'll see which one's lowest. First thing I'm going to do is enter in -1, since that's my left endpoint, right? And you could do this with a calculator as need be, but I think we could do this by hand easily enough. -1 to the fourth is 1, and then the negative coefficient makes that -1. -1 squared is 1 times 8 is 8, so 1 plus 8 plus 10, and so that looks like that's going to be 17 is the output that we get. Similarly, we'll plug in 3. 3 to the fourth is 81, so we got -81. 3 squared is 9 times 8 is 72, and then adding 10. So we've got 82 minus 81 is an output of 1. So these two endpoints, you've heard me in class or you've seen me in class talk about, here are our two endpoints on this given interval. Okay, so endpoint 1 and endpoint 2, check. Check. We now want to find any and all of our critical points that occur between -1 and 3. And the way that we do that is simply find the derivative and then set that derivative equal to 0. So f prime in this case, using simple power rules, it's going to be -4x to the third and 16x. And then that's a cubic equation, so there should be 3 such critical points. Now, they might not all be on that given interval, but we'll find them at least. By setting this equal to 0. So -4x cubed plus 16x equals 0. I'm going to factor out, actually, let's just divide both sides by -4. We get x cubed minus 4x equals 0. We take out an x, let's scroll this down a little bit, take out an x as a GCF, and we're left with x squared minus 4. And feel free to go a little bit faster through this as you like. I'm just kind of taking my time and showing my steps here. But what you'll notice is that we can quickly find, I'm thinking 3 roots. And I wrote the number 3, sorry about that. But we can find all 3 of our roots here. So x is going to be equal to 0 or plus or minus 2. Now, on our given interval, you'll note which ones are on that interval and which ones are not. Of course, 0 is. But -2 is not, +2 is. Okay, so these two critical points, we want to determine, what their corresponding y values are, and then we'll just see which one is the lowest since we're looking for the minimum. And similarly to how we did it earlier, we just plug and chug. We don't have to have a calculator to figure this out. All we do is just say, okay, well, 0 is easy enough. It's going to be an output of 10. That's that aforementioned y-intercept. And then if I plug in 2 to the fourth is 16, so I got -16. 2 squared is 4 times 8 is 32. So that's going to be +16, so +26. All right. And since we're looking on this interval for the lowest value, it's either going to occur at an endpoint or at a critical point. And we definitely see it occurring right there at 3, 1. So we would say that that minimum that we're looking for there is indeed 3, 1. And I can't remember if I've got this still pulled up or not. Delta Math, no, I've got YouTube pulled up, but not Delta Math. So anyway, I took this from one of you guys that are in class. This was a current question you were looking at. So I would honestly just type out, it says determine the absolute minimum value. So that minimum value looks like 1 right there. That's the output of the function, which would be lowest. So that's what I would write in for my answer and then click submit. So that being our first example here, what I want to do next is look at an optimization problem. Okay, I've got a couple here pulled up. We'll just look at one here. for this screencast. And again, optimization problems, fellas, are just applications of what you and I have been talking about. We want to, in this process, we want to come up with a function, find the function first and foremost, okay? And then 2, we're going to consider the interval. Consider the interval. You know, in those previous examples, like what we just looked at, there was a given interval. You'll have to just consider the interval here in the context of the problem. Like if I'm dealing with a company and let's say the independent variable is the number of employees. Well, my interval is going to be from 0 to, you know, whatever. It wouldn't make sense to have negative employees, for example. So considering the interval based on the context of the problem. The third thing we'll do is to differentiate. Okay, so differentiate and set equal to 0 to find the critical points. Okay, and then once you find those critical points, just like we said, I would look at chart. Look at the chart of values, just like we did in the previous example. So really, those are our 4 steps to this. If I were going to break it down into a kind of a nice, neat process, those 4 steps are what we want to look to do every time we're in an optimization problem. All right. Now, number 16, we'll just take a peek at his cryptography expert. It's deciphering computer code. This expert needs to minimize the product of a positive rational number and a negative rational number. So let's stop right there and just key in on the word minimize. Okay, to minimize means that I'm going to try and find the lowest point. And so you can imagine on a particular interval here, maybe I've got a curvature that does something like this. Well, I'm looking for that lowest point. That's going to be the optimal, or in this case, the minimal value. Okay, and so when we follow this process, considering the function, let's see if we can first write up what that function of that equation actually should be. It says the product of a positive rational number and a negative rational number, given that the positive number is exactly 7 greater than the negative number. So I'm going to let x equal the positive rational number. Okay. And then we'll say, let's say the positive is 7 greater than, so x minus 7 is the negative rational number. And it says we want to minimize their product. So what would the product be? If we wanted to call this function product p of x, then it's just going to be x minus 7. And that's what we want to optimize. Okay. So what this function looks like is this is an x squared minus 7x. That's a quadratic function. Pardon me. And we're going to want to let me make sure I read. It says what final product is the expert looking for. All right. So if we're going to minimize this function, then let's look at our next step. We've written up our function. It says consider the interval. If x is a positive rational number, then I'm going to be looking on the interval from 0 to infinity. And then when we differentiate, that's an easy enough process to go through here to find p prime, just using our power rule. So 2x minus 7. All right. And then setting that equal to 0 and solving to find our critical points, we've got 2x minus 7 equals 0. You all should be able to find, okay, well, x equals 7 halves. Okay, and then if we've got x equals 7 halves, that's my positive rational number. 7 halves minus 7 would be negative 7 halves. So the product looks like, if we're going to multiply 7 halves, let me change colors so I don't get this off track. My product is going to be minimized. Let's not write it that way. I tell you what, put it up this way. We'll just say x equals 7 halves as my positive rational number, and therefore x minus 7 would equal 7 halves minus 7, or 7 halves minus 14 halves, also known as negative 7 halves. So these are our two numbers, 7 halves and negative 7 halves, and when we multiply them together, what product we'll end up with will be our answer, and that looks to be negative 49 fourths. Negative 49 fourths. All right. If you look at if you consider the type of function that p of x was, it was a quadratic function. What do quadratic functions, generally speaking, look like? They look like a parabola. And so what we're doing is we're finding that lowest value right there. Okay. Let's see here. We've gone 10 minutes and 20 seconds. Why don't we try to do one more of these optimization problems in this example here. Let's look at number 17. And we'll kind of try to run through this rapidly enough. It says a company started selling a new smartphone at a price where X is the number of smartphones made. The parts cost 70. Labor and overhead running the plant's 5,000. How many smartphones should the manufacturer make to maximize profit? Good. The background info here is that profit, and you want to write this down if you didn't know this already, profit equals, okay, revenue minus cost. You and I have talked about that before if you've been in my class. Revenue is the amount of money that we bring in. Cost is the amount of money that we have to pay out. Profit is going to be the difference between the two. And if you're in the black, or if you've made a profit, positive profit occurs when there's more revenue than cost. Excuse me. And if you're in the red, then what that means is that you had more cost than you brought in. And so you have a negative profit, which is, of course, not a good thing. So our profit function is what we want to maximize. All right. So let's figure out what's our function for revenue. The price per cell phone, which we would be given in that first line, is going to be 150 minus 0.1x. That's going to be revenue, the money that I'm making per phone. And then I'm going to subtract from that the cost. Now the cost, it says parts for each smartphone is $70. So 70x would be the cost per phone. And then I also have the overhead to consider, which would be $5,000 a day. So minus 5,000 per day. Okay. So what we want to do is we want to take the derivative of this function, but first simplify it out. So P, our function of profit, let's see here if I can do this rapidly enough, minus negative 70.1x, and then minus 4850. That looks like a good profit function here. Okay. If I've combined my like terms like I think I should have, negative 70.1, and y'all can double check me. Hopefully I don't make a bonehead mistake here. But when we differentiate that, when we find P prime of X, all right, that's going to be just a simple matter of saying, okay, well, that's negative 70.1. And does that ever equal 0? The answer would be no. So I think I've messed something up here. I tell you what, instead of wasting time, let me pause the video and I'll pick back up once I figure out what I've done wrong. It didn't take very long for me to find the mistake that I made here. The revenue is 150 minus 0.1x, and that's times x, because that's the price per cell phone. So like if this is the amount of money that one cell phone costs, and we make x cell phones, we're going to be multiplying to get our revenue. So that's my small adjustment there. And it wouldn't make sense to have a linear profit function to begin with, because then there's no curve, and so therefore no maximization. Our cost is still going to be the same. So we had minus 70x and minus 5,000. First thing we're going to do is distribute, so that obviously is going to change my function and therefore the derivative. So we've got negative 0.1x squared, and let's see, 150 minus 70 is going to be 80. So we got plus 80x and then minus 5,000. We won't have any like terms to go with that constant. And therefore, when we differentiate now, we're going to get negative 0.2x plus 80, which again, we can set equal to 0 and solve that pretty easily. Come over here, and negative 0.2x equals negative 80. If I had set that equal to 0, just subtract the 80 from both sides, divide by negative 0.2. So x equals, let's see here, multiply 800 divided by 2, which would be 400. So x equals 400 is going to be the optimal number of cell phones to maximize profit given the the detailed information right there. Again, when we think about this process, what are we doing? We find the function. In this case, it depended on our prior knowledge of that equation, or that formula rather. We considered the interval. I didn't really say much about the interval, but you wouldn't be making negative smartphones. You know, the interval we are dealing with here is from 0 smartphones a day. Technically, they could just go up to infinity, but you know, there are some limitations there. We differentiated down at the bottom, found p prime, and then we set it equal to 0. Solved for the critical point, and then we don't need to consider the endpoints, because making 0 cell phones a day is going to be less profitable, of course. So anyway, thank you for watching this screencast. I hope that it made sense as far as these two optimization problems. And then again, as we went through one of those homework questions talking about how to set up a chart on Delta Math. So let me know if you have any questions, and I hope you guys have a great day.